Welcome again to this course on the discrete mathematics. Yes, we are still in this part of functions, but today, now this part, we are going to see about the inverse function as a second part of this series of lectures in which we are going to talk about functions. Well, I gave a brief introduction to what an inverse function is. Let's deal with the inverse function further. So can we define the inverse function like you have given with this set that has been mapped? You have the domain and codomain part, and how does the inverse function looks like? Say for example, what is a inverse, f inverse of 2? Yes, this function is not an onto function because 2 is not having a pre-image. Or consider this one. What is the f inverse of 2? Yes, this is not an one-to-one function. So how are we going to decide? Well, which means that the inverse function has some limitations. We can't just use all functions and find its inverse. Inverse function has certain properties. So this is one of the important property of an inverse function. An inverse function can only be defined on a bijunction. You can recall what is the bijunction from our previous lecture. Yes, it's the one which has one-to-one correspondence. Right, let's move on and see more about this inverse function. Let's see here, you have set x and set y. So you are trying to map this x to y. Say for example 1, 2, 3, 4, 5 is being mapped to 2, 4, 6, 8, 10. And you can see what is that function implies. So here, if you want to find the inverse of the given function, the inverse function would be the reverse the process that we have done by sending back set y into set x, just like that. So we can recall what happened earlier. So 1, 2, 3, 4, 5, where 1 is mapped to 6, 2 is mapped to 2, 3 is mapped to 4, 4 is mapped to 8, and 5 is mapped to 10. Now we are going to take the inverse in which the reverse process happens. That's it. 6 is mapped to 1, 2 is mapped to 2, 4 is mapped to 3, 8 is mapped to 4, and 10 is mapped to 5. Well, that looks quite simple. Now let's examine further down here. So one-to-one function as set mapping. So we are going to see there may be some part in which this might be lacking. Does this part has the inverse? We have seen earlier what and how things might be looking at. So this is an example that in which you have 1, 2, 3, 4, 5 and 2, 4, 6, 8, 10, and uniquely they are mapped. All the domains and codomains are mapped uniquely. Then it is possible for us to find the inverse. Okay, here is some of the ways in which we can try to understand pictorially how a function looks like and what will define a function to be an onto function and one-to function or just function itself. How do we determine that? So here is a vertical line intersects the graph of an equation more than one time. The equation graph is not a function. Say for example, if you have the elements like you have a graph and in which you have these are uniquely mapped with x, y coordinates there. Yes, so this is simple function, whereas here you have a kind of elliptical or kind of a circular structure. just a little bit of elliptical part in it, and this you can see they are crossing this both sections, it intersects. As if the vertical line intersects the graph of an equation more than one time, then this equation graph is not a function. You could also try to put the tables in which you can write down these values and check for yourself. Look at this one. Yeah, so they have a unique values there, and this is a function as well. So this is an example in which you can pictorially see how a function looks like. Let's examine further on this function and see more about, of course we are going to talk about inverse function later on. Let's see how to examine what an onto function, what an into function, one-to-one function, and onto functions basically. So you can look at y value there. For example, y is 3, that's where it's crossing there, and see if there is only one x value on the graph. Yeah, this is many to one function, because you can see the two values of x has been mapped to one value of y. That's quite easy to understand. Now let's look at this one. Here again, for any value y, a horizontal line will only intersect the graph once. So you will have only one x value. That's it. So can you see what type of function is that? Well, that is called one-to-one function. We already studied about that part earlier. So as we move further about this, let's consider one more pictorial representations, and as well as from this pictorial representation, let's also examine how the functions can perform the inverse operations. Okay, here is, you have two curves that has been plotted, and again you have the horizontal line. So this is an one-to-one function example. And this is not an one-to-one function. We have seen the previous examples as well there. And again, this one is not an one-to-one function, because for the unique value of y we have two x values that we have seen earlier as well. So sometimes this is called the horizontal line test, and the one which you have seen a few slides back is called vertical line test, and these tests can reveal what type of function is either one-to-one, onto, or just a function itself. Let's see here. Let's if you want to verify the function f and g are inverse of each other. So we are just talking about functions, but here we are uniquely defining two functions, which we will talk more about it later on in the next part of this function series. Say for example you have f of x is x minus 2 the whole square, and x is greater than or equal to 2, and g of x is root x plus 2. And suppose if you have f composition of g, we will come to this point, f composition of g. This we haven't seen yet, but in the next lecture we will deal with that. So for the time being, just I want to tell you briefly what it is. We call it as composition. So in which you have a function, two functions involved. So f composition of g equals root of x plus 2 minus 2 the whole square. Can you see what is happening here? So initially what you had is f of x equals x minus 2 the whole square. That's what you had, and in place of x I am replacing with root x plus 2 there. In place of x I am replacing root of x plus 2 the whole square, and then I am putting a minus 2 there as well. So in fact we are having the whole square over here. So this can see where it reveals to be that nothing but x square. So this part root of x plus 2 is actually g of x, and the minus 2 again comes from the f of x, that part. So we are defining this, and f composition of g and g composition of f. In fact you can see, since both these x are the results of these functions, so if you start with x and apply the function, they undo each other and are inverse. We will consider more on this composition part later on, as I told you. Let us go back to what we are discussing. So here is an example of how a step by step inverse function can be performed. So I appreciate this here. As you can see, first you have to replace f of x with y, then trade the x and y places and solve for y. Yes, then you will get y equals f inverse of x. Just 4 steps. Step 1 is this one. Replace f of x with y. Step 2, trade x and y places. Step 3, solve for y, and y is going to be nothing but your inverse function. Let us try this out. Say for example f of x equals 4 by 2 minus x. First step is to replace f of x with y. Let us replace it. Y equals 4 by 2 minus x, and then comes you are going to trade x and y places. So x becomes 4 by 2 minus y. Now you are asked to solve for y. Let us solve it. So you are taking this denominator towards this left hand side, and then you are trying to solve for y. You are taking x inside and again taking all the parts as such, and finally you get y equals 4 minus 2x by minus x. Y equals f inverse of x. Yes, that is it. F inverse of x is equal to minus 4 minus 2x by x. That is what we talk about. That is it. We find the inverse of a function. I encourage you to use the same similar steps and try to solve some problems by yourself. Let us do some more examples to get familiar with it. Well, you can also say the same one, f inverse of x is 2x minus 4 by x. Okay, as we have just seen the composition part, so f composition of f inverse, that would be interesting for us to see its results as well. So if you try to do it, if you want to have this composition of this 2 function, it would yield x. That is what we seen in the previous slides where we talked about the compositions. As f of x is 1 to 1, first we can see that one, and the domain may need to be restricted there. So a graph of function and its inverse or mirror image about the line. So here if you see f of x, that is y equals f of x and y equals f inverse of x, they are kind of mirror image to each other. and if you try to draw a line that goes right there at the center, linearly separating these two, yes, y equals x. That's the linearity that we talk about. So let's see whether we could be able to find this part here. Y equals 8x minus 16. So here again we go by the steps. As we can see, we are replacing x with y, or switching the part of x and y, and thereafter we are just progressing or simplifying this whole stuff in order to produce the result. Yes, that's finally what you get is here, y equals 1 by 8x plus 2. So that's what we get here for the inverse of a function. We are trying to solve for this one. As I mentioned before, we talked about horizontal test as well as vertical test. A function y equals f of x, if one-to-one function, if and only if no horizontal line intersects the graph of y equals f of x in more than one point. Yes, can you recall that? So for example, the function y equals x square minus 4x plus 7 is not one-to-one on the real numbers, because the line y equals say 7 intersects the graph at 0, 7 and 4, 7. So that's one reason we can use this horizontal line test, so that you can see if a function is one-to-one or not. If suppose no horizontal line intersects the graph more than one point, we can say it is an one-to-one function. On the contrary, if suppose you have y intersects more than one time in the given graph, then it is not an one-to-one function. So let's apply this horizontal line test to the graph below here that you have and see how this applies. Y equals x cube. So let's try to define it. Y equals x cube plus 3x square minus x minus 1. Looks quite bubble strange. Then we are trying to have this one-to-one test on this two graphs. It's clearly seen from the two graph, A is one-to-one because it does not intercept in more than one place, whereas here B is not one-to-one because it intersects in more than one places. So that's the reason why a horizontal line test is quite useful for us to determine whether a function is one-to-one or not. Quite easy, graphically we visualize this whole stuff. So every function y equals f of x has an inverse relation, x equals f of y. Let's see that. Say you have a function y equals the absolute value of x plus 1. So we have the domain and the range. So let's see here. So minus 1 is mapped to 2, minus 2 is mapped to 3, 1 is mapped to 2, 2 is mapped to 3, 0 is mapped to 1. Let's see further on this. So we have an ordered pair of this y equals absolute value of x plus 1 that are minus 2, 3, minus 1, 2, 0, 1, 1, 2 and 2, 3. So that's what been developed by this we have. So if you want to take an inverse relation, we can say x equals absolute value of y plus 1. So if that is the case, let's see whether this fits in. So again we can see 3 is mapped to 2, 2 is mapped to 1, 1 is mapped to 0, and 2 is mapped to minus 1, and minus 2 is mapped to 3 as well. So with this thought, we can see again the ordered pairs of x equals absolute value of y plus 1. There you have 3 comma minus 2, 2 comma minus 1, 1 comma 0, 2 comma 1, and 3 comma 2. Yes. So if you considering these ordered pairs of function f are reversed to produce the ordered pairs of inverse relation. In fact, if you realize that these two ordered pairs of the function, then we can see they have some relations. So if for example given a function f equals 1 comma 1, 2 comma 3, 3 comma 1, and 4 comma 2, its codomain is 1, 2, 3, and 4, and its range is 1, 2, 3. Then the inverse relationship that we are going to have would be 1 comma 1, 3 comma 2, 1 comma 3, and 2 comma 4. So let's see here the domain of the inverse relation is the range of the original function. Yes, we are defining it this way. So the range of the inverse function is the domain of the original function. So we are talking about functions as well as different properties of these functions here, and let's also today we are looking at various graphical models in which we can define the function, we can realize how a function would look like, and we see a relationship that develops as we go on to examine this inverse relations. The graphs of a relation and its inverse are reflection in the line x equals y. Say for example, find the graph of the inverse relation geometrically for the graph of f of x, where x cube minus 2 by 4, that is the given function f of x. Let's see how this works out. So we have the ordered pairs of f are they given by with this equation x cube minus 2 by 4. So let's say you are trying to plot the graph for various values of x. So you are creating this ordered pairs and you are trying to find the inverse ordered pairs in which you are taking the function x equals y cube minus 2 by 4. So how do you expect this graph to look like? Well, this is how, as you can see, they are kind of complementary to one another, and further down if you try to draw this linear line that goes right through the center of these two curves that we have here in this graph. So that's how this relation is being developing. To find the inverse of a relation algebraically, we can interchange the x and y and solve it as we have seen earlier. So finding this relation for this example, we can see f of x is 3x plus 2. So in that case, with the given part that you have, initially you are trying to switch x and y, and after switching this x and y, we are trying to solve or trying to manipulate. Let's see, let's reverse the sides of the equation. So 3y plus 2 equals x, and you're trying to solve for y. That's the idea. And when you solve for y, what you get is nothing but the inverse. To calculate a value of an inverse of a function, subtract 2 and then divide by 3. So that's an suggestions given for you to easily manipulate and simplify this given part. Well, at this time you already been familiar in solving various problems with sets, and now we are switching into these functions where we talk about various properties of the functions, and now we are dealing with the inverse functions and moreover the inverse relations. So these are some of the points that you can take home. Like for example, for a function y equals f of x, the inverse relation of f is a function if and only if f is 1 to 1. That's one of the important points that we have started with this lecture. For a function y equals f of x, the inverse relation of a function if and only if the graph of f passes the horizontal test. We have seen that as well. If f is 1 to 1, the inverse relation of f is a function called the inverse function of f. That's another observation that we have here. And inverse function of y equals f of x is written by y equals f inverse of x. So here is another observation. So from the graph you can see here y equals f of x, and let's try to determine the inverse relation if a function and if it is a function. Let's try to sketch it out. Well, at first this passes the horizontal test, so we could say that the inverse relation of a function is x is there. So if we try to reflect the graph of f in the line y equals x, so we will be producing this inverse of f, that is y equals f inverse. And again, to talk more about this inverse function, so inverse function undoes the function. That's the basic idea. If your function is to multiply by 2, your inverse function is to divide by 2. You are undoing the whole stuff. So inverse of f of x is x. Function is inverse of its inverse function, so f of inverse is x. So let's see here, the inverse of x cube is f inverse of x, that is cube root of x. Right, so that's basically both reveals, you can see whether either we are taking f inverse of f of x or f of f inverse of x, both reveals the same result, that is x. Yes, that's right. Today we have seen different examples here about the inverse function, and again here we have one other example to verify whether a function g of x with x plus 1 by 2 and the inverse of f of x is 2x minus 1. So if you try to have this composition of g of f of x, as we know that we put this value of f of x inside there of g of x and try to find the results. In both cases, whether you are doing g of f of x or f of g of x, the results what it yields is x. So that's the property of inverse function. So it follows g equals f inverse. Well then, that concludes our part of today's discussion where we deal with the inverse function. So I encourage you to solve various problems that are related to the inverse function. Try to understand the basic principle at which a function stays and what are the properties of an one-to-one function, as well as what are the properties of an onto function. How do we examine these functions? Say for example, try to understand the exact horizontal test reasoning as well as the property of the inverse function. Yes, that's one of the part that we have seen the end of this lecture. Yes, there are a lot more to the functions, and there's one more part that left in this series of function which we are going to discuss soon. After this lecture, we are going to have that lecture as well. So until I see you there, have a good time and goodbye.